Okay, hello everyone. First, let me thank Professor Sormani and the organizers for this great conference and creating this opportunity. My name is Surena Hozoori. I'm a PhD student at Georgia Tech, and today I want to talk a little bit about Ricci curvature and contact topology in dimension 3. So first, let me remind you that in dimension 3, we have lots of beautiful results showing that local conditions on a Riemannian manifold, in particular the curvature tensor associated to a Riemannian metric, can lead to topological phenomena. During this talk, assume that M is a smooth, closed, connected, and oriented 3 manifold. One of such results is the famous sphere theorem due to Berger and Klingenberg from like 1960s, and they proved that if M admits a Riemannian metric with 1/4 pitch sectional curvature, meaning that there exists some positive constant C such that all the sectional curvatures of all the planes on the manifold, they're bounded between 1/4 of C and C. In other words, they don't vary that much. Then that manifold it's diffeomorphic to S3, assuming that it's simply connected, or in general, it's a quotient of S3. And after that, Hamilton improved this theorem kind of extensively, and he showed that if M admits a Riemannian metric of positive Ricci curvature, then we can draw the same conclusion. In other words, that manifold needs to be S3, assuming that it's simply connected. So notice that having positive Ricci curvature is a way weaker condition than having 1/4 pinch sectional curvature. So these are some examples of rigidity results that we can get from like putting some local condition on the curvature and getting some global results. But we also have another class of kind of results that they show lack of topological information, or what we call flexibility results. And for instance, Lohkamp in '94, he showed that any smooth 3 manifold admits a metric of negative Ricci curvature. In other words, if you have a manifold, if you have a Riemannian metric with like negative Ricci curvature, you can't have any conclusion about the topology of the underlying manifold. That can be anything. So in other words, it's kind of like showing the lack of information, or you can say it's a flexibility result. So my question is that can we have like similar results in other categories of manifolds? So the previous results were in the category of smooth manifolds, and in particular, I'm interested in contact 3 manifolds, in the category of contact 3 manifolds, and to understand whether local conditions on a compatible Riemannian metric can lead to contact topological information. So obviously, if I want my Riemannian metric to tell anything about this additional structure, contact structure that I'm going to explain about, I need to put some conditions on that Riemannian metric, which is what I call a compatibility condition. And I can ask similar question. Now, can I look at this class of Riemannian metrics and say something about the underlying contact 3 manifold? So first, let me tell you a little bit about contact geometry and these contact structures that I just mentioned. Just talking a little bit about the history. The first roots of contact geometry goes back to late 19th century in the works of Sophus Lee and his introduction of contact transformation as a tool to solve some certain PDEs. He didn't really define contact structures, but the main ideas were developed there. But after that, the similar structures, they showed up in various parts of mathematics, maybe most famously in Hamiltonian mechanics, and then thermodynamics and optics. And the use of such structures, such structures were so common in practice that Vladimir Arnold, the pioneer of Hamiltonian mechanics, he once famously said that all geometry is contact geometry. And that basically means that if you have any kind of geometric question, you can translate it into some sort of contact geometry question. And from around early 1970s, the topological phenomena were observed in contact geometry, and people started to realize that these structures, they have some topological significance. And the first observations were made by Benekin when he was studying knots in contact-free manifolds. And since mid 80s, thanks to many people, including Misha, Gromov, Eliashberg, Giroux, Ednayer, and many others, we have developed many purely topological methods to understand the topology of these structures. And these theories include convex surface theory, open book decompositions, Floor homologies, and etc. So enough of advertising for contact geometry. Let me tell you now what a contact structure is. So let alpha be a one form on M. We call alpha a positive contact structure if alpha wedge d alpha, which is a free form. If we compare it with the orientation of the underlying manifold, then that is positive. And similarly, we call that a negative contact structure, contact form if alpha wedge d alpha is less than 0. And if we call C the kernel of alpha is some plane field, and we call that a positive contact structure, or more specifically, co-orientable contact structure. And notice that by Frobenius theorem, this means that C is a maximally non-integrable plane field. So I could just define the contact structures as maximally non-integrable plane fields on a 3 manifold. So let's take a look at a few examples. So the first example is on R3. So we call this the standard contact structure on R3. C of standard is the kernel of dz minus y dx. So you can easily compute that alpha wedge d alpha is just the standard volume form of R3. And you can easily find the basis for the kernel of alpha and see that the y direction plus rho x plus y rho z, these two vectors, they form a basis for this contact structure. So if we want to visualize this, okay, if you look at this basis for C, at the origin, the plane field is horizontal, because it's spanned by rho y and rho x. And then as you move along y, so notice that along the way, if you start moving along y, the y direction is always in the kernel, but the other vector would tilt as you move along y-axis. So as you see here in the picture, I'm moving along y-axis. The y direction is still tangent, but the other vector is kind of tilting. And that gives me the plane field on the y-axis. But then notice that this structure is invariant in x and z direction. So if you just copy that picture in the x and z direction, that would just give you the whole contact structure on R3. So you can have some sort of, now you have some intuition of contact structures as this kind of rotating plane fields. But you might say, okay, this is just one example. What does it tell about the general case? Well, it turns out that thanks to Pfaff and a theorem of Pfaff and Darboux from late 19th century, all contact structures are locally contactomorphic. In the sense that there exists some locally there exists some diffeomorphisms that maps one contact structure to another one. So in other words, that means that this previous picture that you saw here is an honest picture locally. So that also means that unlike Riemannian structures, contact structures, they don't have any local invariant. because in Riemannian geometry you have curvature, which is a local invariant, which is an obstruction for Riemannian structures to Riemannian manifolds to be similar locally. But in contact geometry we don't have such local invariant. All contact manifolds are locally the same, and that also means that if they carry any kind of interesting information about the underlying manifold, it should be of topological nature. So let's take a look at a few more examples. For instance, on S3, we can have this contact structure, which again we call the standard contact structure on S3. So assume that S3 is a round sphere sitting in C2, and look at the intersection of the tangent space of S3 and the tangent space when you apply J to it, where J is the standard complex structure on C2. So in other words, a C is just a unique complex line which is tangent to S3, in other words. And let me just mention that up to isotopy there exists a Z family of contact structures on S3. So this is not the only example. We have infinitely many distinct contact structures on S3, but this one has some interesting contact topological properties like tightness and symplectic fillability, which I'm not going to talk about in this talk today. And also maybe it's worth mentioning that if you just take one point from this S3 equipped with these contact structures, you would get R3 with the standard contact structure that I described on R3. Okay, another example is on the torus. So look at torus as R3 divided by Z3, and you can define explicitly this Z family of contact structures. So C of n for any positive integer n, you can define the kernel Cn as the kernel of cosine of 2 pi nz dx plus sine of 2 pi nz dy. In other words, as you move from the, if you look at T3 as this like Q with the faces identified, then that means that as you move along Z, so the contact structure is obviously invariant in X and Y direction, but as you move in the direction of Z, the contact structure would do a full twist if n is equal to 1. And if n is bigger than 1, then it would do like n twist as it goes from the bottom face to the top face. And that gives me a Z family of contact structures on T3, and we have like methods to kind of distinguish between these contact structures and show that they're actually different up to isotopy. But before moving on, let me also mention that in the contact structures, we can associate some sort of dynamics to contact structures as well. And since like early 90s, we know, thanks to many people, including Hofer, Helmut Hofer, Zender, and many others, we know that we can use the dynamics of contact structures to study the topology of the underlying manifold as well. So so what do I mean by the dynamics of a contact structure? So let again alpha be a contact form and C be the contact structure or the kernel of alpha. Then we can define a unique vector field X sub alpha such that d alpha of d alpha of X sub alpha is just a 0, is 0, 1 form, and alpha of X sub alpha is equal to 1. So in other words, d alpha is a non-degenerate, maximally non-degenerate 1 form. It has like a one-dimensional kernel. So that means that X is some vector in that one dimension, which is in the kernel of d alpha. And we also normalize this by alpha such that alpha of X is equal to 1. And you can see that this vector field is uniquely defined after choosing alpha. And we call this vector field the Rib vector field associated to alpha. And it's nice to notice that the lead derivative of alpha in the direction of x is equal to 0. As I mentioned, this vector field, or the Rib vector field, is used extensively, especially since early 90s in understanding like topological aspects of contact manifolds that I just mentioned. They're important. And also, like, since I guess 2000, we have even developed like some homology theories, like contact homology, that basically works based on these vector fields and their periodic orbits. So understanding these vector fields is an essential part of contact topology. And so, for instance, if you want to look at the examples that we just discussed, if you look at the Rib vector field associated to the contact structure that I just described, that vector field generates the Hopf vibration after choosing the appropriate choice of contact form. Another example of Rib vector fields, which might be a like more historical kind of motivation, is like geodesic flows. So let's sigma and G be a Riemannian surface, and let UT sigma be the unit tangent bundle of M. Then the okay, I didn't write it here, but assume that sigma is the the tautological one form. We can define this tautological one form, a theta, such that theta sub u of v is defined as g of u, at pi push forward of v, for u being just some point at the unit tangent space of sigma, and v be some vector in the tangent space of the unit tangent space of sigma. And this is the tautological one form on the surface, and on the unit tangent space of the surface, and we can see that this is actually a contact form on the unit tangent space of alpha. And we can see that the associated Rib vector field to this contact form is actually nothing but the geodesic flow on the unit tangent space of sigma. So one way to think about Rib vector fields is that like Rib vector fields are in fact generalized geodesic flows, basically, because these are the most basic and famous examples of Rib vector fields. But on any contact manifold, again, we can define these Rib vector fields and use them to study many questions, in particular the topological questions. But how can I bring the Riemannian geometry into this game? So that's by introducing compatible Riemannian metrics. So now, given a contact-free manifold M and C, we can naturally define a Riemannian metric on M by defining a metric in the following way. Let G of U and V be just 1 over theta prime times D alpha of U and JV plus alpha of U and alpha of V. So in this formula, alpha is just a contact form for C. Theta prime is a positive constant, which we call instantaneous rotation. I'm going to explain about that. And J is just some complex structure defined on C. So C is just some plane field, and we can define some complex structure defined on C, and then we can extend it to the whole tangent space of M in the sense that we can first project along after fixing alpha, we can project along the Rib vector field of alpha, which is transverse to C, and then then apply this complex structure. So we can extend it naturally to the whole tangent space. So after choosing alpha, this positive constant instantaneous rotation, and this complex structure on C, we can define this Riemannian metric. So this is basically similar to the way that you define Riemannian structures associated to symplectic manifolds. Whenever you have a symplectic structure and some compatible complex structure, then you can naturally pair these two to get a Riemannian metric, right? But in this case, in the case of like 3 manifolds, or generally like odd dimensional manifolds, this is the similar thing that we do. So now instead of a symplectic form on the whole manifold, on the whole like tangent space, we have D alpha is basically a symplectic structure when restricted to C. So again, on C we pair D alpha to and J to form a like Riemannian structure on C, and then we extend it to the whole tangent space by adding the second term, which is alpha of U and alpha of V. And we call this a compatible Riemannian matrix associated to some contact manifold. So for instance, in the previous examples, the round metric and the flat matrix, they're compatible with the standard contact structures that I just described on the sphere and torus, respectively. So a few properties of compatible metrics. So what was this mysterious like constant theta prime that I just called instantaneous rotation? So theta prime, you can easily observe that is just d alpha of u and v, where u and v is an oriented orthonormal basis for C. So basically, theta prime is this constant which measures how fast, like the plane field is rotating with respect to being integrable, right? So we had this intuition of contact structures as rotating plane fields. And theta prime is basically the quantity that measures this rotation. So when I say theta prime is a constant positive number, that means that basically the speed of rotation of this plane fields measured by this Riemannian metric is constant. And notice also that not only we know that the Rie vector field, we saw that is transverse to the contact structure, but looking in this metric, this Rie vector field is actually orthonormal to C and is moreover a geodesic field. So this Rie vector field is actually a geodesic vector field on my manifold. So notice that that puts some restrictions on the underlying Riemannian metric. So we describe this round metric as being compatible with the standard structure on S3. We describe the flat metric as the as being compatible with the contact structures I described on the torus. But you can also ask, okay, can the hyperbolic metric also be compatible with some contact structure on some hyperbolic manifold? And here, because of this property, we see that the answer is no. Because Zerev in 1999, he proved that there is no geodesic field on a closed hyperbolic manifold. So in other words, hyperbolic metrics, they can't be compatible with any contact structure on closed manifolds. So notice that we do have contact structures on hyperbolic manifolds as well. Okay, I didn't mention, but actually we have contact structures on any manifold. But the point is that if you want to put a Riemannian metric on that hyperbolic manifold, which is compatible with the underlying contact structure, then that Riemannian metric, it can't be hyperbolic, although the underlying manifold is a hyperbolic manifold. So in other words, we have some geometric obstructions for compatibility as well. So what do we know? So the geometry of these metrics has been studied basically extensively since mid-20th century by many people, including David Blair, Chern, Hamilton, and Perron, and many other people. It's kind of studied extensively in depth. But the point is that we don't know a lot about the global geometry of these Riemannian metrics. So remember that in the category of smooth manifolds, it was like the global geometry that helps us go from like the local conditions to topological phenomena. But it turns out that we know very little about the global geometry of compatible Riemannian, although their geometry is very well studied actually. But we know a little bit. So what maybe most importantly is the beautiful contact sphere theorem that basically tells you that the equivalent of sphere theorem that I mentioned in the beginning of the talk also holds in the contact category. So this is due to Ednayer, Komendrachik, and Masood in 2012, and then improved by G and Huang 1 year later. They showed that now if we have a contact manifold equipped with some compatible Riemannian structure, so M, C, and G is a contact manifold, and some compatible Riemannian structure, some metric which is compatible with this contact structure, assuming that M is again oriented close, assuming that it's also like simply connected, then if the curvature of this compatible metric is 1/4 pinched, then we can conclude that this contact manifold is nothing but S3 and the standard contact structure on S3. So remember that I mentioned, so okay, obviously the underlying manifold being S3 is just a classic sphere theorem. So because again, this compatible metric is some metric and it has like 1/4 pinched sectional curvature. So the underlying manifold is S3 by the like classical sphere theorem. But remember that I mentioned that we have a Z family of distinct contact structures. So here the compatibility of this Riemannian metric is yielding the underlying contact structure to be the standard contact structure that I described for you, not those infinitely many others. So it's interesting to see that the contact sphere theorem holds in the category of contact manifolds as well. And it's natural to like have this conjecture that can we have a similar theorem to Hamilton's as well. So this is a conjecture that if again M, C, and G, let them be a like manifold equipped with a contact structure and a Riemannian metric which is compatible with that contact structure, assuming that it's again oriented, closed, and simply connected, then can we conclude from the Ricci curvature of this compatible metric being positive that this contact manifold is the S3 with the standard contact structure. So this would be the equivalent of Hamilton's theorem in the category of contact manifolds. And that's an open question. So the theorems that I just discussed is that they motivate kind of studying the Ricci curvature of this of compatible Riemannian metrics. And in particular, I can ask what functions can be realized as the Ricci curvature of the, let's say, Reeb vector field of a compatible metric. Because we said that again, Reeb vector fields, they also play a very important role in the study of dynamics and topology of contact manifolds. So understanding the Ricci curvature of these vector fields is maybe the first step towards understanding the Ricci curvature of these compatible metrics, and maybe going towards the conjecture of the like equivalent of Hamilton's theorem in contact category. So I want to talk about, for the rest of my talk, I want to talk about the Ricci curvature of Reeb vector fields. So first, let me mention that it turns out that the Ricci curvature of Reeb vector fields, it turns out to have kind of interesting geometric interpretation. So we can see that the Ricci curvature of the Reeb vector field, assuming that the metric is compatible with the underlying contact structure, is equal to the determinant of the second fundamental form associated to the plane field C. So remember that whenever you have a plane field and with some Riemannian metric, you can define a second fundamental form for that plane field. So remember that this second fundamental form is a bilinear form that is equal to the covariant derivative of V in the direction of U, paired with N, and then apply the metric to it. So n here is the normal direction. So basically, it's the covariant derivative of v in the direction of u, and looking at the normal component of it, where u and v are, they form a orthonormal basis. Sorry, they don't need to form an orthonormal basis. It's just a bilinear form defined on C. So looking at the normal direction of this covariant derivative, we can get this second fundamental form. And remember that maybe you're more used to this second fundamental form when you had it, like, let's say, surface in a three manifold, or which is basically when the plane field is, like integrable. So remember that if C is integrable, then you have this famous theorem of Gauss that tells you that this determinant of second fundamental form is actually equal to the sectional curvature of C. So this is the context that I'm sure everyone is slightly familiar with Riemannian geometry has seen, like second fundamental form. But it turns out that we don't really need the integrability of this plane field to define the second fundamental form. We can always define it, although in the general case it's obviously not equal to this sectional curvature of C. And in this very specific case, actually, we see that this determinant has some interesting interpretation. This determinant is actually equal to the Ricci curvature of the Riemann vector field. And looking at this characterization, it gives us a kind of formula to understand like Ricci curvature of Riemann vector field. We can compute that this Ricci curvature, we can compute through the determinant of the second fundamental form that it's equal to theta prime squared over 4 minus these two positive terms, that they measure basically the magnitude of this the covariant derivative of x in the direction of E. And here in this formula, E can be any vector on the plane field C. So if you choose any vector E, then computing this formula would give you the Ricci curvature of the Riemann vector field, because basically if you want to compute the determinant doesn't depend on the choice of like orthonormal basis for C. So that's basically why this formula doesn't really depend on the choice of unit vector field that we assume for C. But notice that these two terms that we're subtracting from theta prime squared over 4, they're both positive, and in particular that tells us that the Ricci curvature is actually bounded above by theta prime squared over 4. And it's also important to understand when this Ricci curvature is equal to this kind of maximum or this bound. We can see that the Ricci curvature is equal to theta prime squared over 4 exactly when the Lie derivative of the complex structure J in the direction of X is equal to 0 at a point. Okay, and notice that, as I mentioned, all the contact form alpha is also invariant under X, and theta prime was also like constant. So basically, this is also equivalent to when the Lie derivative of G in the direction of X is equal to 0, where G is the compatible Riemannian metric. So touching this maximum has some important geometric meaning. So, but this is the characterization of touching this maximum at one point. So it's natural to see what happens when we have the Ricci curvature is equal to this maximum everywhere. And it turns out that we will get a rigidity result in this case. So when using previous works of like Rukimbira, Thomas, Niederkruger, and some other people, we can see that when the Ricci curvature is equal to this maximum, theta prime squared over 4, like everywhere, then we can draw conclusions about the contact topology of the underlying contact manifold. And that we can see that it's a very, very restricted case. So when we have this condition, then we can see that M and C is virtually contactomorphic to a boost-Wang vibration. So first of all, when I say virtually contactomorphic, that means that after going to a finite cover, it's contactomorphic. So after going to a finite cover, we can see that M and C needs to be a boost-Wang vibration. I'm not going to talk much about like boost-Wang vibrations, but let me just mention that whenever we have an S1 bundle over a surface sigma, and if we choose any like non-zero element of the second cohomology, like integral cohomology of sigma, then we can associate some like contact structure to this S1 bundle, and this where these S1 fibers are actually generated by the Reeve vector fields of that contact form. Okay, but the upshot of this theorem is that I'm not going to tell much about boost-Wang vibration, but the upshot is that these are very, very few examples. Basically, this is like very, very specific case of contact structures. Okay, so it's a very, very restricted case when we assume the Ricci curvature is equal to that maximum everywhere. And we can also see that we have nice contact topological rigidity properties on these contact manifolds like tightness and symplectic fillability, which are important properties for contact topologies. I don't have time to get into them, but the upshot is that this is like very, very rigid and a restricted case when we make that assumption. But what about the polar opposite? What if we assume that the Ricci curvature is always less than this maximum, never touches that maximum? Does that put any like a restriction on the contact topology of the underlying manifold? So it turns out that if this contact manifold M and C, let that be any contact-free manifold, such that the Euler class of C is not 2 torsion. So 2 times the Euler class of C is not 0. Then we can see that for any compatible metric G with the instantaneous rotation theta prime, there exists some point X on the manifold where Ricci curvature touches that maximum theta prime squared. Oh, that should be over 4, not 2. But anyways. Where X is the Reeve vector field associated to G. So in other words, if the Euler class of C is not 2 torsion, you don't have any chance of realizing a function which is away from this maximum as the Ricci curvature of the Reeve vector field. So we see that we have some topological obstructions realizing an arbitrary like function as the Ricci curvature of the Reeve vector field. But what can we say? What is the best thing that we can do? What about the realization of a general function f of x less than or equal to theta prime squared over 4? So this is the main theorem. So the main theorem that I'm going to discuss is that we can have an almost global realization no matter what the function is. So let M and C be a closed-oriented contact manifold, and let f of x be any function that just respects that upper bound that we need for the, for the Ricci curvature of the Reeve vector field. And let also v be any positive real number. Then there exists a singular Riemannian metric G sub infinity and an embedded compact surface F in M, such that G infinity is a compatible, like honest compatible Riemannian metric, like everywhere except that embedded surface. So let me just also mention that that embedded surface is a surface with boundary. So we can realize, and then the Ricci curvature of x is equal to f of x, the prescribed function, everywhere except that like embedded surface F. And also we can assign the volume of this a singular metric to be equal to the assigned positive real number V. And this is not only this is a singular Riemannian metric. So okay, so again, this is a singular Riemannian metric which is an honest compact metric realizing the prescribed function everywhere except some embedded like compact surface. But also this singular metric has more geometric meaning in it. This G sub infinity, this singular metric can also be realized as an element of L2 completion of the space of compatible metrics. In other words, we can have a Cauchy sequence of compatible metrics L2 converging to this singular metric as well. So let me tell a bit about the proof and like some observations. So the first step in this proof is the local realization. So if you have a function, can we like locally realize it as this the Ricci curvature of the Riemann vector field? So it turns out that any function can be realized locally by just perturbing the complex structure. So notice that I have two parameters to perturb my complex structures. So let's say eta and lambda. Eta should be non-zero, and I multiply. I deform the j of e by eta squared, and then add this like lambda e as well. So I have these two parameters, and it turns out that if you just plug in this if you try to understand the dependence of this Ricci curvature of like the Riemann vector field on these two parameters, that would give us a PDE, and then after some manipulation of that PDE, we can actually locally reduce it to some ODE on a section of X. So if you have locally you have some surface which is transverse to the vector field X, the Riemann vector field, if you again put some kind of initial condition on that surface, again using that flow and solving that ODE, you can actually get a kind of flow box where that your prescribed function is equal to the Ricci curvature, because you can actually reduce this PDE to an ODE which only depends on X direction, basically. So in other words, if you have this again contact manifold with this compatible metric G, and let X be some arbitrary point, and let F be some again function that just respects the upper bound theta prime squared over 4, then there exists a neighborhood U containing X and a compatible metric G star, such that the Ricci curvature of this G star or Ricci star of X is equal to this prescribed function f of X on the neighborhood U, and also we can let G to be equal to G star at that specific point. Moreover, we can actually have that G equal to G star on a section including X, basically, as I mentioned. But to get an almost global realization result, we actually need some topological tools, so which is called open book decompositions. So open book decompositions, that's a topological tool which is used extensively in contact topology, and it turns out we can also use this here to basically extend this solution of PDE to everywhere except some embedded surface, or almost everywhere. So what are open book decompositions? Very briefly, so let me just first mention that according to a very important theorem of Giroux from 2000, contact structures up to isotopy are in one-to-one correspondence with open book decompositions up to positive stabilization. So we have basically some sort of one-to-one correspondence between contact structures and these topological objects, open book decompositions that I'm going to describe in a minute. And thanks to this theorem, we can use these open book decompositions to understand contact topology of contact manifolds. So what is the definition? So an open book decomposition on M is a pair L and pi, where L is an embedded link in M, and pi is just fibration of the complement of this link over S1. And moreover, we want the neighborhood of each component of L, like roughly speaking, to look like a pages of an open book meeting the binding. Okay, so that I'm trying to not get into much technical details. So again, we have a link, and the rest of the manifold can be fibered over S1. And also we need some like nice neighborhood for these links, in the sense that the fibers of this vibration, they meet these links the way that you see in the picture, the way that the pages of a book, they meet the binding of the book. So they we have a nice local structure around of this vibration around these bindings. So we call this link L the binding of the open book, and we call the fibers the pages of this open book decomposition. And looking at this picture, this intuition should basically justify the terminology that we're using. So like as a very basic example, so there exists, so first of all, we know that there exist open book decompositions on all manifolds. I think that's a theorem of Alexander from early 20th century. But as an example, there exists an open book decomposition of S3 with L being just the unknot and the pages being 2 disks, right? So so imagine S3 as like the 1-point compactification of R3 in this picture. And then if you look at the compactification of the z-axis, that would be just the unknot, right? And then you can actually fiber the complement of this unknot over S1. You would get a family of like disks that are going around this z-axis, and they're meeting z-axis in the way that the pages of a book, they meet the binding, right? So this is a example of an open book decomposition, but they can be way more complicated, in general. But the important thing about open book decompositions is that for any contact structure, that's basically part of the theorem of Giroux, that for any contact structure that corresponds to an open book in that one-to-one correspondence that I just described, we can assume that the Reeve vector field is transverse to the pages away from the binding. So in other words, Giroux tells us that whenever you have a contact structure, you can build an open book decomposition associated to it in a way that for some appropriate contact form alpha for that contact structure, the Reeve vector fields are transverse to the pages of that open book decomposition. And in particular, for instance, you can see that the open book decomposition that I just described on S3 is actually compatible in the sense that I just mentioned with the standard contact structure on S3. So now that we have this condition, we can go back and finish basically the idea of the proof of almost global realization. So remember that when I was trying to do the local realization, I could manipulate that PDE into some sort of ODE that depends only on X direction. So basically I can look at X direction as time when I'm solving an ODE. And then by putting some initial condition on some section of that vector field, I can solve that ODE and extend the solution to a flow box around that section. Right? But now we have this open book decomposition that all the pages are actually transverse to this Reeve vector field. So now I can put the initial condition on one of the pages and then use this again, that ODE, and look at this X vector field as time and solve that ODE and extend the solution to all of this go through to all of these pages. And I can go let's say I start from F naught in this picture, and I keep moving in the direction of X because I know X is transverse to these fibers or these pages. And I keep solving, extending the solution of my PDE until I get back to F naught. So here B is the binding, and this is a schematic picture. These pages are meeting the binding, and let's say I put just some this initial condition on F naught and use the flow as time to solve my PD, and until I get back, because this is a fibration over S1, so I can extend this until I get back to F naught. But when I get back to F naught, there's no reason for my solution to match my initial condition, so I can't guarantee that I can extend my solution over F naught again. And that's basically the idea of the almost global realization, and the compact surface that was showing up in the theorem is actually nothing but this one page of this open book decomposition associated to my contact manifold. And also I can kind of, instead of, I kind of did this crudely, but I can also do this in a kind of nicer way. I can realize, make this procedure like instead of having a like kind of surface of singularities, I can also do this procedure in a kind of nicer way, and as a, in a way that it doesn't produce singularities, but we don't realize the prescribed function around the neighborhood in some epsilon volume neighborhood of that page. And using that and using the works of Brian Clark, we can actually realize this singular metric as the limit of an L2 Cauchy sequence of compatible metrics. So basically, I can do this in a kind of gradual way, in a sense that in the limit, I will have this wall of singularity instead of just having it once. So finally, let me end my talk with this question that I saw that, first of all, I saw that on this, I have some topological obstructions to, to prescribe any function for any contact manifold. So there are some topological subtleties. But then I saw that I can have an almost global solution always. And that basically means that I can reduce the question of having global solutions to the question of if I can get rid of that surface of singularities, which was a compact surface. And it leaves me with this natural question that, okay, under what conditions can we have a global solution? Or under what conditions can I get rid of that surface of singularities in that theorem? Okay, this is the end of my talk, and thank you very much for listening.